Hey, this is Horner. We're going to look at 7.4, gravitational torque and center of gravity reading guide. The answer to the first one says two spheres are connected by a rigid but massless rod to form a dumbbell. The two spheres have equal mass. So even though the sizes are different, their masses are the same. So we're going to go ahead and put M for each one. Because they have equal mass, we know that the center of gravity will be right in between them. And that is how you would explain your reasoning. The two spheres are connected in number 19 by a rigid but massless rod to form a dumbbell. They're made of the same material, so this one's going to have a bigger mass than this one will. And we can mark a location closer to the bigger mass because that's where it would balance. We would want to make sure that our pivot point is right near the bigger mass so that the smaller mass has more length, so the torques are the same. So you have to really be careful with it. For the next one, it wants you to look at this device, this little angled piece here, and it says mark the center of gravity of this object with an X. So one of the things that we need to do is we need to mark the center of mass of each one of the two equal pieces. So if I make a line that divides the two pieces and then I kind of find a spot somewhere in the middle for each one, that would be the center of mass of the two. If I draw a line between the two and then I put my X would be where the center of gravity of this entire object would be. So by symmetry, it just lies on this midpoint. This is very similar to a boomerang. If you throw a boomerang, it will pivot around this X. It won't pivot around this corner. It'll actually pivot around the X. So that is where the center of gravity lies. It is just on the midpoint of the line created by the two center gravities of the two objects themselves. So that's the easiest way to look at that one. Let's go ahead and go to the back side. On the back side, we're going to do the first two, and then we're going to skip over the very last one because it's one that's a little bit more complicated that we really don't need to know how to do for this course. So for the first one, it says find the coordinates and mark the center of gravity for the pair of masses using the center of the 3 kilogram mass as an origin. So if this is x equals 0, this would be x is equal to negative 40 centimeters. So at this point, we're going to use a new formula. This formula is the center of mass for this system is equal to the first mass times its distance from the origin. So we're just going to put R1 plus, plus the mass of the second object times its distance from the origin divided by the sum of the masses. So that's m1 plus m2. So sometimes you'll see this equation as the sum of the mass times the radius divided by the sum of the mass. So for this one, the center of gravity, or the center of mass, is going to be equal to our first mass, which is 1, times its position, which is negative 40. And then we're going to add that to the 3 kilogram mass times 0 because it is at the 0 point. And we're going to divide that by 1 plus 3 since those are our two. If I do that, I'm going to end up with a value of negative 10 centimeters. So that would be somewhere about here, closer to this mass, but that's our actual value, negative 10 centimeters. So we've marked it there. If we look at the next one, it's essentially the same thing. Notice that same masses, same distance, but now we're using our origin as the 1 kilogram mass. So let's do the same thing we did before. The center of mass is equal to the mass of the first thing, which is 1, times its position, which is 0, and we're going to add that to the mass of the second one, which is 3, times its position, which is 40, and we're going to divide by the sum of the masses, which we said was 4. What do we get this time? We get 30 centimeters, but that's from this side. So you'll notice that the position has not changed. It's still at the same position. It's just very, very different. So how do the coordinates compare? We use a different coordinate system. So we've used a different coordinate system, but we know that these two locations are the same location. And that is what's just really kind of what I wanted you to know about this section. Now, I will go ahead and answer this last one just for those of you that are interested. If we do the last one, now what they've done is they've taken our picture that we had up above and they split this mass into two equal masses of 1.5 kilograms. They want to know where is the center of gravity of the X piece. So where along the x-axis is the center of gravity? It's actually at the same spot. It's at 30 centimeters. So remember, this is our starting position. This over would be 40. So we would have a center of gravity on the X right here. The center of gravity for the Y direction really has not changed. It's very slightly higher, but not really, because you have a 1.5 mass on the Y and a 1 on the Y, and then you have a 1.5 mass up here separated by 10 centimeters. So it's only shifted by a very small amount. So there's really no effect on either of the components. That's a little bit deeper than what we probably need to go into, but that's essentially what you would see. So we are going to say that the center of mass will not change for these. So if you have some objects that are initially in one position and they shoot to another position, that center of mass will actually be the same as long as you've moved them symmetrically. And for this one, we've moved symmetrically because we've just half the mass and then we've made that distance between them about 10 centimeters. So that is the end of 7.4 in your reading guide.